Show you number one equations of the tangent through the pole, which problems 5 and 7 pertain to, and then easy areas of polar graphs, which 13, 15, 17 pertain to. And here we go. Tangents through the pole. Okay, so suppose I gave you this problem. R equals sine of 3 theta. And I said, get me the equations of the tangent through the pole. Well, first of all, what specific point is the pole?
Origin.
Yeah, the origin, 0, 0. It's the place where r equals 0, and that's only at 0, 0. So at first blush, you think, okay, getting the equations of the tangents through the pole, all I need to do is find at what theta value I go through the pole, and then let her rip, you know? So at the pole, r equals 0. So all I have to do is set the sine of 3 theta equal to 0. But here's the interesting thing. I've got many theta values for which this is true, correct?
Yes. Yeah.
I mean, because for the sine of whatever to be 0, I need whatever to equal 0, or whatever to equal 180 degrees, or whatever to equal 360 degrees. And I have to keep going. If I'm going to go from 0 to 2 pi, if someone tells me, hey, you know, theta is between 0 and 2 pi, then I got to keep going, because right now I'm only at 120, you know? So I got 3 theta equals 540, you know, and so on. So I end up with theta equals 0, theta equals 60 degrees, theta equals 120 degrees, theta equals 180 degrees. And at this point you can see that, you know, they're going in increments of 60 degrees. Let me now show you graphically why it ends up looking this way. Let me graph y equals the sine of 3 theta. Okay, and because the biggest r can be is 1 or -1, I'm going to go a -1, 1, -1, 1, and then here it comes. Boom, boom, boom.
3 panels.
Now, there's something I want you to notice. Did you notice that this little thing here kept graphing? Like if I can show you again, here, let's change this to a 6. Oh, I changed my mind. Change it to 0. Well, watch how it graphs and how in the upper right-hand corner it keeps thinking. Okay? That tells me that it's graphing at once and then just repeating the graph. And so one ability you need to have is to know what theta values, you know, to use to graph. And the best way to do it, there's a way to do it algebraically, but I would prefer you not to. Just try different numbers. Let's go from 0 to 180. And there it is. Do you see I get the whole graph from 0 to 180? So now I know, okay, I'm just going to go from 0 to 180 because then I get repetition. Well, let's try something even better. Let's go like 120. 0 to 120. Okay, 0 to 120 is not enough, right? So that tells me 0 to 180 is the way to go. And that's the way I want you to do it, since again, here it is almost completely unlikely that you'll get a problem like this where you don't have the aid of your calculator. So go ahead and just do that. So now I'm going, hey, I don't really have to go keep going. This is enough. You know, in fact, 0, 60, and 120 is enough. Alrighty? So now that I know my theta values, remember, you need to get 2 things for the equation of a tangent line, point and a slope. I know my theta values, so now I'm going to get my x and my y. My y is going to be sine of 3 theta times sine of theta, and my x is going to be sine of 3 theta cosine theta. Alrighty. So now I can get my x comma y's, correct? Wait, wait, I already know my x comma y. So what's my x comma y always going to be?
0, 0.
Yeah, 0, 0. What am I doing? 0, 0 for all of them. So I don't have to get my point. I know my point. It's 0, comma 0. Now I have to get my slope. Okay, dy dx, which is dy d theta over dx d theta. And now I'm going to get the derivative of this guy, which is going to be 3 cosine 3 theta sine theta plus sine 3 theta cosine theta over 3 cosine 3 theta cosine theta minus sine 3 theta sine theta. Okay? So I got my derivative. And now I'm going to plug in dy dx evaluated at theta equals 0, this guy. If I stick in a 0, are you okay that that guy's 0, that guy's 0, that guy's 0, and this guy is 1? So I get, or 3 rather, so I get 0 over 3, which is 0. So for theta equals 0, the equation of the tangent is, since the slope is 0, it's going to be just y equals 0. That's when this guy starts from here and comes out like that, I got a tangent line right there of 0, of y equals 0. Hey, let's do the same thing for theta equals 60 degrees. dy dx evaluated at theta equals 60 degrees. Cosine of 180 is negative 1, so I'm going to have 3 times negative 1 times the sine of 60 degrees, which is rad 3 over 2, okay, plus the sine of 180, which is 0. Then I've got 3 times the cosine of 180, which is negative 1. So I've got 3 times negative 1 times the cosine of 60, which is a half, okay, minus 0. So I end up with rad 3. So that means I'm going to have the graph y equals rad 3x. I want you to see, okay, when this flashy dot, when my angle gets to 60 degrees, do you see how the flashy dot is going to 60 degrees? Here's 65, here's 60, here's 55, you know? Do you see how it's passing through right there? Can you see that, guys?
Yeah.
Essentially, the part of my graph that's passing through the pole is this part of the graph now, and this is at theta equals 60. And so that's why the equation of the tangent line ends up being y equals rad 3 x, okay? And then finally, when I do it for 120, just trust me, dy dx evaluated at theta equal 120 degrees ends up equaling negative rad 3, so that the line is y equals negative rad 3x. And that's because as I come around to 120 degrees, here's 115, there's 120, there's 125. So do you see, I'm right there on that part of the graph. So I end up having this tangent line here, y equals a negative rad 3x. So you get to do a couple of problems like this on tonight's homework, where you're going to have to find the theta values where your function hits the pole by just setting r equal to 0, find those theta values, then get dy dx and plug in those theta values to find your slope, and then your equation will be y times that slope times x. And I don't have time to have you guys do a problem like this. Is there any question or problem on this? Just the 2-step process. Number 1, set r equal to 0, find the theta values. That's the step 1. And then step 2, get an expression for dy dx, and then plug in those theta values. And then step 3, the equation is going to be y equals the whatever slope you find times x. And that's it. That's all you got to do for those. But the problem is it's a kind of involved process. Alrighty. Then hey, it is time to do easy graphs. Areas of easy graphs. Just a second. I don't have my notes out.
You won't have to do it.
Do I have them out already? What the heck? Here, just a second. I'm trying to find my notes. Where's my area notes?
It's been a while. I didn't choose five. That's why I didn't know five. I don't want to do much.
Aha! Sorry, guys.
Physically. If she was
Now, you're going to get areas. You're going to get areas of polar graphs. Whereas before, to get areas, you would add up a bunch of rectangles, correct?
Yeah.
But not now, no siree. Now you're going to add up a bunch of sectors. You're not adding rectangles anymore. You're adding sectors. You're adding pizza slices. You're going to be adding up a bunch of infinitesimally thin pizza slices. Okay, and that's it. And the equation, I'll even tell you what is going to end up happening. Okay, the area is going to end up being the integral from the initial theta to the final theta of 1/2 r squared d theta. That's the formula that you will mindlessly use. Okay, and that's it. That's the name of that tune. And so. Let me show you where that formula comes from, and let's do a couple of easy areas. Tomorrow we'll do hard areas, alrighty? But I just want to let you know ahead of time, that's what's happening, okay? So first, I want to derive the area of a sector, okay? This is something you learned about in geometry. You know the area of a circle, right? The area equals pi r squared. And you also learned that if you had a sector or a pizza slice of some angle theta, you learned in geometry if theta was in degrees, okay, if you're in degrees, then the area of a sector ends up equaling whatever the theta is divided by 360 times pi r squared. Do you remember learning that? Where if this theta happened to be, let's say this theta was 65 degrees, and you wanted to get the area of this pizza slice, well, that's 65 degrees out of a total of 360, right?
Yeah.
360 would get to the whole circle. 65 is just a portion of it. So yeah, your area would be 65 over 360 times pi r squared. You okay with that? That's what you learned in geometry in 10th grade or 9th grade or whenever you took it, or 8th grade. Well, if you're in radians, this is a different story. in radians, the area of a sector is going to be the angle theta in radians divided by the entire circle, which is 2 pi radians, times pi r squared. But look, the pi's cancel, and I end up with just 1/2 times r squared times theta. So that's the area of a sector in radians, 1/2 r squared times theta, right? Because the pi's cancel. So, yes?
Sorry, so we're going to be in radians mode?
Yeah, when you punchy in the calculator and get these integrals, you're gonna have to be in radians mode. Because any calculus that happens is in radians mode. So you're gonna have this weird situation where when you graph this, to look at the graph, you're gonna have to be in degrees mode. But when you do the punchy to do your actual calculus, you're gonna have to be in radians mode. Because whenever we take integrals or derivatives, you have to be in radians mode. Yeah, absolutely. Okay, so let me show you what's going to happen. You know, let's say I have some polar graph that looks like this, okay? And let's say I want to get the area from theta equals 0 to theta equals 90 degrees. Let's say I want to get this area, this crazy amoeba-looking area, okay? The way I'm going to do it is by adding up sectors. I'm going to add that sector to 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 that sector. I can add up these 1, 2, 3, 4, 5, 6, 7. I can add up those 8 sectors, right? I can call this S1, S2, S3, all the way to S8, okay? And so I can say the area is approximately equal to, let's say this is delta theta. Let's say each one of these thetas is identical. So every delta theta is identical. I didn't draw it that way, but let's just pretend. So every little sector has an angle of delta theta. Then, you know, my area is going to be S1 plus S2 plus dot, 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 all the way to S8. And so my area is going to be 1/2 times this r, let's call this r of theta, you know, that r, 1/2 times r1 times delta, r1 squared times delta theta, plus 1/2, let's say this guy, we choose this r, we'll call it r2, so it'll be some, you know, whatever theta is, r of theta, but what I'll call that r2, r2 squared, delta theta plus dot, 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 all the way to 1/2 r8 squared times delta theta, which means it's going to be the sum of the 1/2 r squareds, as r, you know, here is n goes from 1 to 8 here, times delta theta. But you know what comes next. What am I going to let delta theta get really, really close to? Yeah, 0. I'm not gonna make 8 sectors. I'm gonna make 8 million sectors, right? 8 billion, 8 trillion sectors. I'm gonna have delta theta getting really, really close to 0. And when delta theta, the limit as delta theta goes to 0 of delta theta, I don't know. But as delta theta gets closer and closer to 0, what does it magically turn into? Yeah, d theta. And this summation, if we start adding up a billion things or an infinite number of things, it becomes an integral. And so I get the integral from theta 1 to theta 2 of 1/2 r squared d theta. And this is where this formula comes from. You're just adding up a bunch of sectors, okay? How are you going to determine theta 1 and theta 2? I'll tell you by your graphing calculator. You're going to do it entirely graphically. You're going to determine what those bounds are by using your graphing calculator. So hey, let's go ahead and you know, let's do an example. Example number 1. Get area of one petal of r equals 3 cosine 3 theta. Okay? Step 1, you have to graph it. And please be in degrees mode, because no one in this class thinks in radians. So please get your graphing calculator and graph it now. If you don't have a graphing calculator, you must get one. What is that, 3 cosine 3 theta? Okay. And I'm going to go to, I don't know whether to go to 180 or 360 or whatever. I'm going to go to 360. Oh, I got to be from -3 to +3. Oh, it just keeps going and going and going. Wow, it really keeps going. Let's go to 1. I think this will be from 120, 0 to 120. Here we go. Nope, not quite. I guess 0 to 180. All right. But it doesn't matter if you graph it where it repeats itself, but I like to have it. Okay. Next, you're going to have to use the graph to find bounds. Find the angle bounds. I'd like you to please press trace and tell me, what should the bounds of my integral be?
0 to 60 or 120 to 180 or 150 or 30 to 90.
Okay. Is everybody okay? One choice would be 30 to 90. 30 to 90. Let me show you. You start at 30 degrees and you start adding up all these sectors, all these pizza slices. As I go from 0 to 90, then I come back down and I go away. And so I'm adding up this pizza slice to that pizza slice to that pizza slice to that one, to that one, to that one, to that one, to that one. You see how that works? You're not adding up rectangles, you're adding up pizza slices. There's another choice. You don't have to go from 30 to 90. What other pair of angles could you go from?
150 to 210.
150 to 210, let's trace. Okay, 150. Yeah, oops. Yeah, okay, 150 to 210 will work. My guy stopped at 180, but if you go 150 to 210, that's fine. Is anyone thinking of 90? What is that? 90 to what is that, 150? Anyone want to do 90 to 150?
No.
Okay, well, you can go whatever you want. By the way, let's say you're the type of person who's just in love with having 0 on their integral. I can go from 0 to 30. What would I have to do to my integral, though, if I want the area?
Multiply by 2.
Yeah, multiply by 2, right? Because 0 to 30 will get me this guy from there, and then 0 as I go to 30, I'm adding up these sectors, and then finally I get to here. So 0 to 30 is fine. Just make sure you double your area, okay? So I'm actually going to do that. I'm going to go 0 degrees to 30 degrees. But remember to double your area, okay? But if you want to go from what was it, we said 30 to 90, if you want to go 30 to 90, that's fine. So the area is going to be, for me, it's twice the integral from 0. But I got to tell you what, do I put 30 degrees here? No way. Now that I'm going to have to take an integral, I'm going to have to put pi over 6. And then 1/2 r squared d theta. So this is gonna be 2 times the integral from 0 to pi over 6 of 1/2. What is r? 3 cosine 3 theta squared d theta. And so now I can get my answer. And I'd like you guys to go ahead and punch that in. Let's see what you get. Make sure you're in radians mode. You see how I was in degrees mode? I'm gonna have to go to radians mode now. And so now I got 2 times the integral of 0.5 times parentheses 3 cosine 3 theta squared.
So Shane,
Yeah.
if you plug in x for theta, will it be the same?
Yeah, but if you're in radians mode, it should be saying theta. But if you plug in x, it's fine.
Oh no, because my calculator.
Oh, yeah, then just do x, that's fine. Yeah, x is fine. Alrighty. Syntax, what? Oh, I forgot to put theta. Shoot, stupid. There we go. 2.356. I'm getting 2.356. Is anyone getting that?
Yeah.
Okay, yay, and is this the point I say bye-bye?